Let me also pull up mine. I've not got access to my PC right now, so I've got to use OneNote online to look at the solutions I did. Cool. Okay, we've got some responses in. So okay, so on the left we have Danny's response. Assuming n is a node index starting at 0, void delete nth if n is less than 0, or n is greater than or equal to size, then throw a new illegal argument exception, because then the n is out of range. If n is equal to 0, first equals first.next and return. So we're just setting the linked list. Imagine this is our linked list and this is our second element. We're just setting our linked list to this instead of this. Cool. But if n is not equal to 0, node current equals first. Current index equals 0, while cur is not equal to end. If current index is equal to n, current equals current.next, return. If current index is equal to n, then we want to... if n's 0, would we want this line here? I'm just thinking about... Yeah, so I'm just thinking with this current equals current.next, if we set the... Oh, actually that makes sense because we're removing that node. Cool. And then we just return. So if we reach the current index, just replace the node we have in question. So just point this to this, and then we're basically removing the nth, well, the node at index n. And then if it isn't the index, then we want to set current to current.next. So we want to keep going to the next element, and we want to increase the current index by 1. And we throw in the legal argument exception if we get down here outside of the while loop and we've not returned anything, because that would mean that the n value they've returned is pointing to a node that doesn't actually that can't be removed. This solution looks good to me. Does it look like there's anything missing here? For loop because it's count controlled. Yeah, but it wouldn't be that useful using a for loop. You could just stick all of this in a for loop. But I think with linked lists, for me personally, while loops are just a lot. They make more sense. Can you explain what's going on? Yeah, so the idea is we have a linked list and we want to remove a node with a specific index. So say we want to... This points to this, this points to this, this points to this, and this just points to end. And this is our linked list. So yeah, the idea is if this is our linked list, all of these nodes have indexes. This is index 0, 1, 2, 3. Say we want to remove the node at index 1. All we're doing is we're just going to, if n is 0, first equals first.next, n is not equal 0. Let's say we pass it with n equals 1. So n is 1, we go down here. Node current equals first, so this is current. And then current index is 0. I'll just say ci equals 0. Well, current is not equal to n, so this isn't equal to end. Then 0 is not equal to 1. So we're going to say current equals current.next. So now current will be pointing to this node here. And current index will increase by 1. and then we're saying if current index is equal to n, which it is, 1 is equal to 1, then we're saying current equals current dot next. So we're wiring this to here. My only issue with this solution is that we're actually getting rid of the index plus 1. We're not getting rid of the index 1. So I think we might have to modify this solution a bit, because it tells us that it starts at 0, and so if we pass in n as 1 into here, we want to get rid of this node, not this node. So how could we fix this pseudocode? Okay, so current is not equal to end. Solution uses 2 pointers, but not sure if you need 2. Right. I see how you've sort of done that with 2 pointers. That's one way of doing it. I think that makes sense. Let me try and find my solution. Summer 22. Okay, this is what I did. I did type it up, but yeah. So if n is less than 0, then it's an illegal argument. So we just throw an illegal argument exception, and we return. I'm not sure if we'd actually need this line because this kind of implicitly returns most of the time. Okay, so then int I is 0, node target equals this dot first, so it points to the first node in the linked list, and prev equals end. So yeah, essentially what Danny said and what Adwit's done is similar to what I've done. I've kept track of 2 pointers. One points to the target and one points to the previous one so that we can then go back and update it. So we start by pointing at index 0. While I is less than n, so this just means while we aren't at the node we want to remove, then we want to set... Oh, I found an error in my code, if anyone could spot it. But we want to set the target to the target.next, and we want to set prev to this. So prev will be set to this, and target will be set to this. And then in the next run, target is going to be set to this, and prev is going to be set to this. And so when we're at the thing we want to remove, we can look at our prev value, and we can say prev equals prev.next. So this will look at this and point to whatever that is. And we'll essentially get rid of that target. The garbage collector will pick that up. But one issue I found with my solution is if I is equal to 0, or if n is equal to 0, prev.next is going to throw an error because we set prev to end initially. So I think one thing we should do is, do we assume that? I mean, I think given a pointer to a node n tells us that some node exists. But maybe just in case an initial node doesn't exist, you could have something like if n is equal to 0, return. Or just return n.next. Or Actually, this wouldn't even work, would it? Because this wouldn't actually update the value of n. So I think we have the assumption that we have that this is a node that they're actually inputting. This is a reference to a node. Yeah. Or I guess you'd say if n is equal to 0, this dot first equals this dot first dot next, because that's overriding the value we're storing in this dot first. Yeah, the input's an int. The input's just the index. I just realised that. Size. Do they say we need to actually modify? Right. It does maintain a variable size. So I also forgot to do size here. So what we'd have somewhere here is just size minus minus. Yeah. Cool. Okay. So yeah, this was my solution with a few tweaks. Yeah, if n is less than 0, we throw in a legal argument exception. If n is equal to 0, we actually want to just set this to this, and we also want to return inside there. But if it's not equal to 0, set I to 0, target to this dot first, and while I is less than n, we keep updating target, and we keep updating prev, until the target is what we want to remove, at which point we look at the prev, and we just update the next value in the prev to whatever target's next was. And then we decrement size at the end, as Danny's reminded. Awesome. Yeah. So the reason why this one wouldn't work is just because we're actually deleting the thing at n plus 1, not the thing at n. And let's take a look at this. If n is less than 0 or first is equal to null, throw an illegal argument exception. Int c is equal to 0. Node, okay, I'm guessing that's a reference to a node. Node prev equals first. While c is less than n, prev equals prev.next and c++. That looks like that should work as expected. Well, c is less than n. Prev equals prev.next. So if we passed in n as 1 here, and we set prev to this, while c, 0 is less than 1, prev equals prev.next, so that's going to set it to this. And then we're going to say prev.next equals prev.next.next return. So, correct me if I'm wrong, Hux, but would this remove the thing at index 2 instead of index 1 if we passed in 1 as the argument? Because this would say prev.next equals prev.next.next, so this would say this. I'm not sure if I've read that wrong. But it would go into this loop once. It would say, because initially prev is being set to first, and so we're doing prev.next. It should be c less than or equal to n. Yeah, I think if we did c as less than or equal to n, that would end up deleting 3 and saying this goes to this, I think. Wait, yeah, no, and if we start at c equals 1, I think it would skip 1. I think the main way people have done it is just keeping track of some extra variable prev. We need to write a separate part for deleting the start limit. Yeah, so that's why I'd probably add an exception saying if n is equal to 0, then first equals first.next. And then, yeah, so I think something like this would probably work, where we have if n is less than 0, throw. If n is equal to 0, we handle that exception explicitly saying this dot first equals this dot first dot next, then we just return. But if n is anything other than 0, then we can do this, where we keep track of some prev value, which is like a lagging pointer, basically. And so if we find what we want to remove, we use this lagging pointer to decide what to remove before it, or what references to update, if that makes sense. How would you delete the first? So I think the idea is the abstract data type has a node pointer called first, which points to the first node of the list. So that isn't part of like an argument or anything. You can access that with like this dot first or just first. And then you just want to overwrite that value. You'd assume this is like some global value that's been declared in the data type, not in this method locally. So you just say something like this dot first dot next equals, or this dot first equals this dot first dot next, or just first equals first dot next. Oh yeah, and Phoebe's just reminded me we need to also size minus minus here. Delete enters a method in the list class, right? So you don't need to pass in the list. Yeah, exactly. We have access to that list via first inside the function. All we're passing into this method is the index we want to delete. Yeah, exactly, Danny. Okay, shall we go on to question 2? Yes. I love how we spent 20 minutes on one question. Tells you a lot about DSA. Okay, question 2. Assume that this abstract data type has two different methods. I'm guessing that's not supposed to be there. Two different methods to delete all the elements from the singly linked list as follows. Void delete all from start. While sizes are more than 0, we just keep deleting the 0th element. And void delete all from end. While size is more than 0, delete nth size minus 1. Give the complexities of these two methods in big O notation and explain how you derived them. Write the pseudocode for a much simpler and more efficient method to delete all elements from the list. Okay. So the first method deletes the first node. We update the first pointer to the node that the first node was pointing to. Search for it P1 plus O1. Wait, what's P and O supposed to be? Okay. Okay, let's paste let's paste in Okay, let's just so I mean looking through these, if we keep deleting nth 0, we know that the time complexity of our delete nth is going to be O of n. So this part is O of n, and we're going to be doing it while the size is more than 0. So we're going to be doing it n times. So this whole thing would be O of n squared. And this one, this is also O of n. And this is also going to be O of n. So this is going to be O of n squared. Oh, right, yeah. So this one's not actually going to be, because we're always deleting the 0th element, this is going to take constant time. So this would actually be O of n times O of 1, which is O of n. Yeah, good shout, Danny. Cool. Okay, so hopefully they're correct. And then the second part of the question, write the pseudocode for a much simpler and more efficient method to delete all the elements in the list. And so Danny's much simpler version looks quite good. Delete all, we just set the first to end, so we set it to a null node pointer essentially, and we just set the size to 0. And I don't see any problems with that. If anyone else does, let me know. Looks good to me. Beautiful. Okay. So, I mean, all it means to delete everything is to remove any references to it. Because we have a garbage collector, as soon as we remove a reference or a pointer to something, it's essentially just forgotten or dropped. So all we're doing with this line here is we're dropping our reference to our original first node and we're just overwriting it with end. So our first node, say it was pointed to by this first variable, and this was pointing to a bunch of other nodes, and this was pointing to another node. As soon as we overwrite this first to point to end, then we get rid of this pointer, and all of this is not pointed to anymore, so it all gets garbage collected. Cool. Why was the last one in over n squared? The reason the last one was in over n squared was because while the size was more than 0, so n times, we did something which would take over n, because delete nth takes over n, because we have to loop all the way to the end, and then replace the pointer just before the end. And then we have to loop all the way to the end, and replace the pointer just before the end, and loops all the way to the end, so that's over n, and we're doing that n times, so overall that's over n squared. Cool. Let's move on to question 2. Whereas, yeah, the reason this one was over n was just because this is constant. If we're just getting the first one every time, we know we're going to go into this while loop a constant number of times, just like one time. And so we're not even going to go into this while loop. We're just going to hit this if statement. So this is constant. And so it's over 1 times over n, which is just over n. Okay, let's have a go at question 2. Right, question 2. The following is a pseudocode for a recursive algorithm to print values stored in a binary tree in no particular order. Give the pseudocode of a non-recursive algorithm to print the contents of a binary tree with a complexity that is no worse than the above recursive algorithm. You may use a stack abstract data type in your answer. Hopefully this is a big clue as to what we want to do. Stacks, DFS, depth first search. So let's paste in some solutions. Okay. So, print tree, and we pass in our initial node, and then we declare a stack. If t is not equal to null, stack.push t. While the stack isn't empty, we pop the top node off the stack, we print the node's value, and then if the left is not equal to null, we push that onto the stack. If the right's not equal to null, we push that onto the stack. And what this essentially is just doing is a depth first search. If we're not too familiar with that, say we had a binary tree like this, a DFS just says, okay, let's search this one, then this one, then this one, then we backtrack and search this one, then we backtrack and search this one. Actually, we wouldn't actually search the... Okay, yeah, so first we do that one, and then we look at the left, and then we look at the left, and then we go up and look at the right, and then we'd go up and look at the right, and then the left, and then back up. So it's kind of just using a stack to visit all of the nodes in this order. As opposed to a depth first search, we have a breadth first search, where if we wanted to use a queue, we could also do this entire thing with a queue. And pretty much the code for that would just be changing this to a queue, changing that to a queue, and just changing all of these to a queue, and that would be a breadth first search. I think a question does come up later where we have to use a BFS, but yeah, this DFS answer looks correct to me, if there's no issues with that. Yeah. Phoebe, if you want BFS, it's just this, but change all the stacks to queues, and that's it. While queue isn't empty. Q.dq. Yeah. Cool. One way you can also do it, and one way how I decided to do it, it would work the exact same, I believe, but oh, never mind. No, I did it how Ollie did it. Yeah. But yeah, one way you could do it is just do the null check in here, and then just get rid of this if statement, and that way you can just say if node is equal to null, just don't do anything. Else push both of its children. But either way, this works as well. Yeah. Okay. Right. 2B. What was 2B? Okay, 2b, consider an ABL tree of positive integers that does not allow duplicate values in the tree. The insertion of the value 10 into a minimal such ABL tree, that is of height 3, triggers a double rotation. Okay, so draw the diagram of this tree both before the insertion and after the insertion. The best thing to do here is, first let's just draw a minimal ABL tree. So, height 3, we know height 0 is going to be 1 node. Height 1 is going to be 2 nodes. Height 2 is going to be this plus 1, so 4 nodes. Height 3 is going to be 7 nodes, because it's these 2 plus 1. So we want a tree with 7 nodes. Okay, so we have a root node, and we know our height's 3, so let's just make a three extra nodes on the right here, like a linked list. And then all you have to do is you just have to balance the nodes recursively. So this one's balanced, this one's balanced. To balance this one, we just need 1 here. To balance this one, we just need 2 here. And I believe that is our minimal ABL tree of height 3. Okay, so the insertion of value 10 triggers a double rotation. And so if we want to trigger a double rotation, we're going to need to insert something here. Hopefully we can see why that's the case, because if we insert something here, then we're going to have to do a right rotation and then a left rotation. So let's say this is where our 10 goes. We need to make sure that this 10 is going to fit here. And I believe we should, I believe we can fill in the positive integers just to write in exactly what's swapping. So let's just label these 1, 2, 3, 4, 5. Okay, so if the 10's going to eventually come here, we want this to be greater than the 10. We want this to be 12. And if this is going to go on the right of 10, we want this to be something like 14. So in this case, if we insert a 10 here, it's going to end up making... Let's just demonstrate. Okay, so if we insert the 10 there, we're going to have to do a right rotation first, bringing this 14 down, bringing this 10 up. And then we're going to have to do a left rotation. We're going to have to bring this 12 down, bring this 10 up, and nope, something's gone wrong. This has to be less than 10. This 12 should be something like an 8. Okay, so yeah, if we insert a 10 in this case, we have to first do a right rotation, and then we have to do a left rotation because this node is unbalanced. So we have to bring this 8 down, we have to bring this 10 up, and this 14 up. And so by inserting a 10 into this tree here, it triggers a double rotation. I'd probably say write in the numbers just because then it shows where the imbalance is occurring and why we need to rotate. Because it shows where we'd actually insert the 10. If we just wrote like 10 here, we don't know. I think it's better to write in some example numbers just to show exactly what's going on. Okay, cool. So this would be our before tree without the 10, and our after tree would be this down here. Hopefully we can all see what's happened here. Let me know if there's any questions. But otherwise, let's move on to 2C. No, 3A. Okay. A hash table is implemented using an array of size 8. The objects A to F are inserted in this order into the hash table. The hash 1 and hash 2 values for these objects are table. And it's just told us how it wants us to write the probed indexes. Part 1, or part I. Assuming a linear probing strategy is employed using the hash 1 hash values, list a sequence of addresses probed for each object and draw the final state of the resulting hash table array. So we've got a few correct solutions in chat. Let's just write out how we've done it. So if we have an array of length 8, let's say something like this, and all of these are going to store some value. So first we're going to look at A, because we're inserting it in that order. So looking at A, our hash is 11. Because it's up to 8, 11 mod 8 is going to be 3. So first we'll look in 3. There's a spot in 3, so we'll put A there. Then we'll look at B. B's 1 mod 8 is just 1, so is there a spot in 1? Yes, there is. Let's put B there. I'm going to copy this table down here just for sight again. Okay, so there's space in 1, so we put B there. Looking at C, we try and put that in 1, but B's already in 1. So then we go to 2 and try and put it in 2. There's space in 2, so we can put C there. D, 9 mod 8 is 1, there's no space in 1. So we try 2, we can't put it in 2, so finally we go to 3, and we can put it in 3. E, 0 mod 8 is 0, there's space in 0, so that's fine. And finally F, we can't put it in 1, we can't put it in 2, we can't put it in 3, so we have to put it in 4. And so our result C was in 2, and F was in 4. What am I missing here? No. D would go to 4. This would go to 5, wouldn't it? Yeah. Cool. So D would be here. F would go here. Cool. Hopefully that makes sense. So all we've done is we've looked at a spot. If it's taken, we go to the next spot, next spot, next spot, next spot, until we find a free spot, and then we just stick it there. Yeah. Herx, you might have been looking at the hash too by accident. Okay. So that's part I. Part II, assuming a double hashing strategy is employed, using the hash1 hash values as the primary hash values and the hash2 values as the secondary one, list the sequence of addresses probed for each object and draw the final state of the resulting hash table array. So I'm just going to paste this down as well so we have more space. Okay. Yeah, cool. We've got some more solutions. So hash1, A. So let's get our array back. 1, 2, 3, 4, 5, 6, 7. Okay. So initially for A, we're gonna look at 11 mod 8, which is 3. And so there's space in 3, so we can just put A there. And then for B, we're gonna look at 1 mod 8, which is just 1. And there's space in 1, so we can put B there. For C, again, if we do 1 mod 8, there is not space in 1, so we can't put it there. So then what we have to do is we have to use the secondary hash. So now we do 1 plus 1 times 7. Or I'll write it as 1 plus 7 times 1 mod 8, which is going to be 8 mod 8, which is 0. There's space in 0, so we can put C there. And then we look at D. So 9 mod 8 is 1, 1 is taken, so now we look at 1 plus, our hash2 is 1, so 1 plus, now we look at 9 plus, our hash2 is 1, so 9 plus 1 times 1 mod 8 is equal to 10 mod 8, which is 2. There is space in 2, so we can put D there. And then E. 0 mod 8 equals 0, there's not space there. So then we do 0 plus 3 times 1 mod 8, which is just 3, there's not space there. So now we do 0 plus 3 times 2 mod 8, which is 6, there's space in 6, so we can put E there. And then finally F. 1 mod 8 is 1, 1's taken. So if we then do 1 plus 5 times 1 mod 8 is 6. 6 is taken. And so if we do that one more time, 1 plus 5 times 2 mod 8 equals 11 mod 8, which is 3. 3 is also taken. Yeah, okay, let's try it again. 1 plus 5 times 3 mod 8 is 0. 0 is taken. 1 plus 5 times 4 mod 8 equals 21 mod 8, which is 5. Is 5 taken? No, it isn't, so we can put F in 5. Hopefully, that's what you guys also got. Let me know if this differs to you, your solutions. But the idea is we want to keep increasing the multiplier for this hash2 value, the secondary hash value, until we find an available spot. And so this will be our resulting hash table array. Cool. Okay. I got F in 4. I mean, it would be 6, 7, 8, 9, 10, 11. How did you get F in 4? Load factors. We'll come back to it because I saw how topical of a discussion it was yesterday. I don't want to waste too much time on it. But we're on the last question anyway, so we have some time to discuss that. I was in the car, like, on the way back from London. You guys were talking about load factor. I reached Birmingham, and you guys just ended the stage still talking about load factors. So, we'll discuss it. It's a very controversial topic, I can tell. Cool. Right, let's move on to 3B. Yannick Prim! Yay! Okay. Right. Let's go. 3B. Consider the following graph. Demonstrate the execution of the Yannick Prim algorithm for finding the minimal spanning tree on this graph by writing out a table of the execution steps in the following format, where the first row is already provided. So this is our current distance to the node. This is our node we came from, and then the tick or across depending on whether we finish that node or not. And we've got some solutions in the chat. Let me paste one in. Okay. So, initially, this is just our initial row. We mark A as visited, and that's the node that we finished in that iteration. From A, we can get to D with a cost of 1, and we can get to B with a cost of 3. Cool. And then we look at D. We mark D as done, and from D, we can get to B with a cost of 2, which improves on the 3. We can get to E with a cost of 3, which improves on the infinity. And we can get to C with a cost of 5, which is better than infinity. Cool. And then we look at B. So from B, we can get to C with a cost of 4, which improves on our 5. We can get to D with a cost of 2, which is just what we have there already. We can get to D with 5, no. We can get to E with 5, no. Okay, so that's D done. Then we look at, that's B done, sorry. Then we look at E. From E, we can get to C with a cost of 5. That doesn't improve on the 4. We can get to D with a cost of 3. That doesn't improve on 1. And then finally, we look at C. From C, we can get to B with a cost of 4. No. D with a cost of 5. No. E with a cost of 5. No. So our distances stay the same. And we're left with this last row. I think a few people may have shifted these one cell up or one cell down. I don't expect that we'd get heavily penalized for that because we are just tracing through it. But we also paste in Phoebe's solution. Okay, so yeah, quite similar. 3 infinity 1, 2 5 1 3, 2 4 1 3. Yeah. And I don't suspect. I mean, you in the actual exam, you'd probably want to write this row out again just to show that that's exactly what we're ending on. Because this would be 2D tick, 4B tick, 1A tick, 3D tick. But otherwise, yeah, that looks good. Awesome. Any questions about that?
Shay, are you there?
Yeah.
Oh, we're just saying, column D.
Column D. Yeah.
It's different in the both the solutions you got. Shouldn't it's the second one, right? It should be.
Oh, yeah. Yeah, good point. One thing. So, I think Kirk, you just forgot to put the A here when we visited A there. Even with Dijkstra's, I keep making that mistake. Just remember to upload the. I mean, remember to update the values there. Yeah. But otherwise, yeah, good catch. I think everything else is correct. Cool. But I think that's everything. No more questions on that paper. Awesome. Oh, we're talking about black ups. Oh, good luck. What's the difference? They have to use Dijkstra instead of Prim's. Dijkstra, we want to take the sum of the edge costs. So, for example, we wouldn't just write 2 from D to B, we'd write 1 plus 2 or 1 plus 3. So with Dijkstra, we sum the current distance we have to that node plus the edge cost instead of just the edge cost. I believe that's the only difference because everything else is pretty much the same. What was the kerfuffle about load factor then? Um, Let me save this.